Hi, this is Miss Litton, and this is my wonderful 7th period review students from both classes. Anyway, hi. Hi. Okay, so tomorrow you have a chapter 44 and chapter 45 quiz. It's probably going to be a little bit more heavy on chapter 44 than 45, okay? But that's 45 is pretty simple. 44 had quite a bit of information in it. Remember, 44 was population ecology, 45 was community ecology. And in the chapter 44 part, that's when you learned, though you had those practice worksheets that I've given you that you've had for over a week. Do you think one of those questions is going to come up? I think so too, okay? So we can talk about that too to see if there's any issues on those questions, anything you want to go over with that, and that won't be a problem. Yes?
So we're going to need a calculator on the quiz, I assume?
Yeah.
Okay.
If you're going to do some math, multiplying, I mean, you could do it longhand, but I would use a calculator. It's up to you. All right. So the first part of chapter 44 is kind of things like what is ecology, and I think you should be pretty familiar with that. We talked also about you know, being descriptive and also predictive because we want to look to see what things could happen. We talked about things that affect population, the statistical analysis. We look at the numbers, and one of the things we talked about was the density. Meh. So remember, density, you can figure that out. That's easy peasy. In fact, one of your practice questions that had you figure out the density, I think of turkeys or something like that, if you've done it. Whisper to your bio buddy right now, have you done both worksheets already? Yes or no? I'm saying whisper so you know I won't judge you. Okay, so now come back to me. So you would know what I'm talking about if you had done those because all you have to do is take however many you have and divide it by that area, right? That gives you density. The second part that you want to be familiar with are the way organisms are distributed, okay? And we looked at a couple different things. We talked about, on this one, if you remember, you have regular, or what was another way that I said instead of regular? This doesn't say regular. What does it say? Uniform, exactly. And then uniform, and then what's the next one over that we have here? What? Random. And then what was the third one we had? Clumped. Which one is the most typical? Clumped. Why?
Resources aren't always equally distributed.
Yeah, there we go. Resources aren't always equally distributed, so they'll be clumped around those resources. When the amount of resources is evenly distributed, what differentiates between the first two is just how much competition there is. Okay? And we can go over that as well. And then the third part was rate of growth, and we had two different growth curves. So we talked about in environments, there are both abiotic and biotic portions of that. That should be pretty easy, right? Living and non-living. And here's some other examples of those. And then we went in and discussed regular, random, and clumped. In clumped, your resources are not equally distributed, and so they're around those resources. Here, they're in regular and random, they're evenly distributed. Which one has more competition? Regular. Regular is high comp. Random is low competition, but overall the resources are evenly distributed. Here, you're around, you're clustering, maybe it's a watering hole or a feeding source of some sort. Could the way they distribute themselves and their dispersal patterns, could that change over their lifetime? Yes. Okay. And I think I gave you an example, some little shrubbery. Okay, young ones are clumped, the medium shrubs are random, and then by the time they're uniform by the time they're mature desert shrubs. So that's telling you the environment is fairly uniform, right? And there's high competition by the time they're mature, and that's why they get in that uniform arrangement. Questions or concerns you want to ask me about that? No? Okay. Next, we started going into natural rate of increase. So we talked about birth rate minus death rate. Again, if you have done those sheets, then you know what I am referring to. We talked about maximum R, okay, where you're really making your birth rate go up and your death rate go down. And we talked about what kind of things will affect R. And we talked about when do you start reproducing, how many offspring do you have, how often do you reproduce, and what are your chances of survival. Which then we transitioned into talking about cohorts and survivorship curves, how likely you are to survive until the end of your life cycle. And we are type 1, which means most of us that are born live our full lifetime and then we die when we're old. The opposite of us would be type 3. Who's a type 3 besides the oyster that you see there? Yes, plants, okay? You're right, that's what you said. Because in order for those plants to take hold, that seed has to find what? Good soil, right? Some will fall among the rocks. Some will fall among the thorns, and they will not find good soil, so it will not sprout, will not germinate. Okay? And then things that are usually prey, they're either going to be prey, it doesn't matter if they're young or old, somebody's going to eat them, so they'll lose throughout their lifetime, that you can, they'll die off. Okay? So those are survivorship curves. How long will I survive? Okay? And then we looked at age structure diagrams. So I'm trying to think of ways that you will remember that. Age, and how is that age structured? Do you have more youth or more old people? Or the same amount of young people and the same amount of old people? Is your population, based on your age structure diagram, will your population size go up, go down, or will it remain stable? Populations that are going to increase in size, their age structure diagrams look more like a what? Pyramid. When you have a lot, very youthful, because all of them are going to move from pre-reproductive to what? Reproductive. Okay? Pretty easy on this part, you okay? All right. Then we talked about, do you have one single reproductive event in your lifetime, or do you have multiple reproductive events? And most mammals have multiple reproductive events, right? And you would classify us as being Kselected. Do you remember that? Where this could be what? R-selected. Once and done. You're only thinking about this moment, making as many offspring as you possibly can. What's something else you could tell me about R? Small. What else could you tell me? High number of young? Is that what you're going to tell me? What else are you going to tell me? You don't care for your young? Are you going to say something about that? You remember those things? Okay, whereas Kselected, these tend to be what? Large, right?
Less offspring.
Yeah, less offspring, more care. Okay, good. Colonizers versus competitors, right? All of those. All right, so then we started looking at two types of growth curves, and I'm going to pick one that has them both on there. Okay, so here is your exponential growth curve. Eat and drink, for tomorrow we may die. Okay, and then this would be your logistic growth curve. And your logistic growth curve is going to start deaccelerating. It's still going to have an exponential phase, right? You can see they both have a lag. They both have exponential. But what starts to slow down the growth rate of the logistic growth curve is it's running into what? Carrying capacity, limited resources. So now we're going to start to want to hover around that carrying capacity because it can only support so many individuals. Okay? Where this one, it could continue indefinitely. Anyone could, as long as you had unlimited resources. But generally, these are going to hit a hard crash as a result of overshooting their resources. Okay? And then we talked about carrying capacity. So then you have a change in the number of individuals over time is going to normally just be R times N. And we know what R is. R is going to be the birth rate minus the death rate. And N is just how many you have. You know, so if I say the birth rate is 0.6, the death rate is 0.2, then what's 0.6 minus 0.2? 0.4. And then I say the number of individuals in your population is 270. You would take 0.4 times 270. Yes? What is 0.4 times 270? What is it? 108. So listen to me. That was the change in population over time. So the change is 108. So what's the population going to be next year? What would you do? 270 plus 108. So that would be 270, 378, right? Did I do it right? 378. That is the change in the population. Are you okay with that? Now, all you do is you say, what's the change in the population over time? Well, here is my growth rate, R, times what am I? That tells me the change. Take that number. Maybe it's a negative number. Because why would it be a negative number if the death rate is higher than the birth rate? Then this is going to be a negative change. My delta change is going to be a negative number. Let's say it's negative 12. I would subtract that away from 270, right? You all right? Now, same population, except I'm telling you that the carrying capacity is 500. How would this have been altered if I had known that there was a carrying capacity? Yes?
The maximum number that the population can be.
Right. So now I'm still taking my R, which we calculated. I said birth rate was 0.6, death rate was 0.2, so we said R was 0.4. I still know my population is still 270, because I'm doing it over now with the carrying capacity. Now I just have to multiply it by this. What did I say the carrying capacity was? 500? 500 minus 270 over, what's my carrying capacity? 500. So figure that out, because we just need to take 108 and multiply it by that. What's 500 minus 270 over 500? Just that number. 500 minus 270 over 500. What is that number? What is it? 499.46. Point what? 0.46? You good with that? So now take 108 and multiply it by 0.446. What is that? 49, do you agree? I haven't done it. I'm just making up numbers.
It's
49.68?
Yes.
So then what do you think we want to say? Probably going to have to go with 50 on that. It depends if they say it in the nearest tenth or the nearest whole number. Okay? So why is it when I do it this way, I get 108, but when I do it this way, I get 50? I'm closer to the carrying capacity, so it's putting the brakes on it. If I had unlimited resources based on my birth rate minus my death rate, my population would have increased by 108. So I take 270 plus 108, and that would have been my population next year. But lo and behold, I still have the same birth rate and death rate. I still have the same population size, 270, but I'm getting very close to my carrying capacity. So I'm going to be reduced by what? Competition. So therefore, I will only increase by 50. That's what I would predict. So now it's 270 plus 50. What is that? What is it? 320? Now find out, what do you predict the population will be the next year? Work it out. What would be the population the next year? I don't know, because I'm not working it out. So, are you ready? You ready, ready, ready? Yes. Okay, so now what's my starting population? What's my R is still the same, it's still 0.4. Okay, but what's my N now? It was 270 plus 50, so what was it? 320. And now when I do K minus N, I'm still 500, but now I'm minus 320 over 500. So what did that equal? What is it?
46, yeah.
46. So the next year, Do I get any feedback on that? Anybody else got the same thing?
Who's trusting me?
Yeah, no, let's verify. You all should have calculators or access to calculators.
Yeah.
You agree? Okay, so now this year, the following year after that, they only grew by 46 instead of 50. Why? Closer to the carrying capacity. Right? And then what would I need to do? I want to know at the end of the second year, what is my population size?
366.
Yeah, because I'm going to take 320, what I was at, add it up there, and now I'm at 366. And then I can figure it out for the next year too, right? And I'm predicting if I was going to make a trend, the number I add to my population each time is what?
Less than the last one.
Less than the last time, because I'm approaching the carrying capacity. Yes?
So for the AP test and or the quiz, we have to memorize that formula or it's given?
No, remember you have a formula sheet. It's on your formula sheet.
Is that also the quiz?
Yeah.
Awesome.
Yeah. But I don't really think you need, right?
Just in case.
Yeah. If on the quiz I was giving one of these questions,
Theoretically.
I wouldn't need a formula, because I would expect you to know R times N and R times N, K minus N over K. I mean, but yes, I could put that up there. But I would expect you would know that.
I would hope so.
I would hope so, yeah. Okay, because those are the key parts you need to know. Okay, if you haven't done those questions, those practice questions, I would encourage you to do that. Okay, the first one, they just give you the answers at the end. The second one, they show you how to do the answers. Okay, and you're welcome, you know, and I would recommend that you still work them out, even if you didn't. If you had problems with those, you can come. I know I worked them out somewhere. Yeah, I worked them out even though they gave the answers, so you can see how I worked them out. That's no problem. They're right here. Okay. All right, so I'm going to go back to. All right. So then following that, we looked at, and this part's pretty easy, I think, is looking at two different factors that can regulate population size: density independent and density dependent. Our selected species tend to get impacted by density independent, right? Our selected. And then density dependent factors are the things that are regulating the K, right? K selected species, all right, typically. Now, things like tornadoes and floods and those type of things, they happen regardless of the size of your population, because those are just abiotic factors that have nothing to do with life, okay, other than they can kill it, right? But biotic factors, these are things that are more likely to occur because your population size is what? Big, and you're under competition. Things like parasite spreading and disease spreading. It's because you're competing with one another. You're in close proximity. Competition is going to increase as a result of that. What other ones did we give? Get to that. Competition. We talked about, this chapter's on population ecology, but we're also having a quiz on community ecology. So this would be community ecology technically, because they both affect the other. Their numbers affect each other. If there's not enough prey, then the predator numbers are going to go down and vice versa. However, okay, things like drought, an abiotic factor, can regulate the number of hare that you have, right? Or sorry, who's our prey? Moose that you have here, if they don't have enough to eat, right? An abiotic factor could impact them as well. Talked about parasite, we talked about disease, we talked about our selected species like the cockroach, opportunistic, small, we already went over that. We went over Kselected. They tend to be competitors, not colonizers, equilibrium, large, slow to mature. Then we went in on human population, and we talked about zero population growth is birth rate minus death rate. Numbers have really climbed. They're starting to level out a little bit, but you see a great difference between what and what? More developed countries versus less developed countries, right? You can see a big difference. And we said, in conclusion, after when we analyzed everything, that the greatest impact on reducing population size was the what? Education of women. Okay, education of women. Okay. We looked at age structure diagrams, and maybe instead of just looking at our overall money that we have as a country, we want to consider other things like our ecological footprint. Okay, that was chapter 44. And then chapter 45, I think is probably a little bit easier. Oh, look, there's your quiz.
Open that. You can open that too.
Go ahead, open it, start it.
Well, just let us take a few pictures.
Yeah.
We can do the review.
Yeah, you're serious about things. Dun, 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 dun. All right, 45, we talked about community. We talked about you have to look at not just the components, like a list of who lives there, but you also have to look at their abundance. What would be another word for abundance? Density, good. Then we talked about all about islands. What could you tell me about islands? Bigger islands that are closer to the mainland have the greatest diversity. Good, so that's island biogeography, good job. We talked about the difference between a habitat and a niche. Habitat is where you live. Niche is what you do. And we said no two species can have the exact same niche for any length. What's going to happen? Somebody's going to die, somebody's going to live, and or?
No, partially.
Well, that can come later, but what? Resource partitioning. Okay? Now, because you're going to exploit different resources, this can lead to character displacement. Remember Darwin's finches and the different sized beaks? So, okay, because you're trying to exploit different resources, then you might need different adaptations, right? For those resources, if you're eating the big seeds versus the little seeds, you might need a big beak versus a little beak. So this can lead to character displacement. I have a bigger beak, you have a little beak. Got to be one or the other. Hot is helpful, hot water is helpful, and cold water is helpful, but lukewarm, I spit you out of my mouth, right? Okay, so either be hot or be cold. Okay, so that promotes character displacement, and character displacement can lead to speciation. You were there, you just jumped there, already there. All right, so we looked at some organisms are generalists, some are specialists, and when you have change in the environment, especially rapid change, and who can cause the most rapid change? Man, because man is bad, right? And that impacts the specialists, right? We talked about a realized versus fundamental niche, okay, where you could live in your home, in your house, okay? Where do most of you live? In your room, okay? And we talked about competition when two different species want the same thing. And we talked about the competitive exclusion principle. Where did I put it? Somewhere. Is that it? Yeah. No two species can occupy the same niche for long. We looked at character displacement. We looked at predator versus prey. We looked at the way they cycle, but we already knew that. We talked about coevolution, pushing each other to evolve because of your interactions. We looked at defenses by plants, things they could have, sharp spines, leathery leaves, poisons. We looked at things like warning coloration, don't eat me because I'll make you sick. We looked at things like what? Camouflage of the prey. You could have camouflage of the predator. We looked at fright, mimicry, and there were two kinds of mimics. Do you remember the two kinds of mimics? Batesian and Mullerian. Okay. What is a wasp and a bee? Mullerian, because they both have stinga, right? Malarian, stinga. Batesian is a lie. Will you fall for the bait? I really don't have a stinger, but I'm looking like somebody who has a stinger, so leave me alone. Fall for the bait. Okay? That's Batesian. That's not why it was named that. It was named after a guy. I'm just trying to think of ways to help you. Yeah, help you out. Then we revisited the idea of the symbiotic relationships, and we looked at parasitism. What's another one we looked at? Mutualism, like those cleaning relationships. What else do we look at? Commensalism. Good. And you want to be familiar with an example of each of those. Okay, then we talked about continental drift impacting the organisms that can live in different areas. We talked about disturbances within our communities. It's not necessarily a bad thing. It's a cleaning house, right? It's getting rid of the understory so you get you get rid of the waste so you can get new plants and new organisms living in there. And replacement, normal ecological succession, and where you have small plants and then that makes it available, increased soil and nutrients for bigger and bigger and bigger until you get this climax community. And I took you through several different models, okay, that we looked at, in that succession we classified it as either primary or secondary, and secondary succession has soil. Okay, that's going to happen faster than primary succession because you're on bare rock. Good. Okay, and we talked about pioneer species, and we looked at fire wiping things out, and then we looked at all these different. You don't have to memorize all of these. You know, one promotes the other one inhibits the other one tolerates it, and we looked at you have more species closer to the equator, and we know because think words that have productivity in them. Can you think of words?
Production.
Good.
Oh yeah.
Gross and net primary productivity. Remember that? GPP, MPP, respiration. So where you have the highest net primary productivity, where the plants can make the most sugars, if you have more sunlight, you can have more producers, which means you can have more consumers at every level, at every trophic level. Okay, and that's when we went into what are producers, what are consumers, like herbivores. I think these are pretty easy, omnivores and carnivores. But then we went into that energy flows and nutrients cycle. So we followed energy through, and we looked at food chains versus food webs, right? Food chains looks at a single pathway, but in reality it's all about food webs. Yeah. And they look like this. And then you could have grazing food webs, or you could have detrital food webs where it starts with decomposers, or they could overlap. And then you take them and stack them up. Okay, and you can have these, you stack up the trophic levels, and then you'll have your ecological pyramids. Because the bottom of the pyramid would be the producers, then the next level would be the primary consumers, then the secondary consumers, and the tertiary consumers. And we said those pyramids are going to have really big changes because how much gets passed on each time?
10%.
About 10% gets passed on each time. So then you stack those up as trophic levels. Looks something like this, but in reality more like this. Okay, and then that brought us to our cycles. So we had the reservoir where it's stored, exchange pool, and community. Water cycle, I think you know. Only weird words maybe are aquifers, you know. But transpiration, you know, right? Precipitation, condensation, you know those. And man screws it up by polluting it or drilling for the water and causing sinkholes. Here's your GPP, MPP, R, right? Okay, the next cycle we talked about is the carbon cycle. And you know things, what are things that are going to increase carbon in the atmosphere? What kind of things are going to increase carbon in the atmosphere? Okay, combustion. Okay, deforestation, sure, but I'm looking combustion, cellular respiration, decomposition. These all increase CO2. What's the only thing that, all increase CO2. What's the only thing that decreases it? Photosynthesis. So therefore, if we remove the plants, like what you were saying, that's going to increase it. Okay, and then that brought us into our discussion about global warming. Good. Then we went to a sedimentary cycle like phosphorus. Phosphorus is a limiting factor. It's not normally in rocks. What gets it out of the rocks? Weathering, erosion. Could man facilitate that process? Yes. Not only could they erode the rocks faster, but due to chemical plants that we have or our domestication of farm animals, increasing the amount of runoff from their manure, all of those things can cause over-enrichment of a lake. And the problem is it's a limiting factor, so it could cause an algal bloom, which is fine. Oh, you just picked up your GPP and your NPP, but eventually that algae is all gonna, who works on them? Decomposers. Decomposers do what process? Cellular respiration or photosynthesis? Right, so they're gonna suck what out of the lake? And the lake will die. Okay, so we have to be careful of that, and that's called eutrophication of a lake. Okay, and then the last cycle that we did was the nitrogen cycle. Okay, so there's three big parts. Nitrogen fixation takes it from the air into a solid. Nitrification makes that solid into a form that plants can use. And then denitrification is removing it back to the reservoir in the air. All of these require what? Bacteria. Okay? Exceptions is when we make nitrogens and put them in the soil, like fertilizer, or we do yeah, we don't control that though, but all the rest of the time it is. So let's review the nitrogen cycle, because that's the only one I think you might struggle with, if at all now. You know it so well. Here we go, hands in the air, hands up. So you take nitrogen gas, you do nitrogen fixation forming ammonium. Okay, nitrogen fixing bacteria do that. What's our next step? Nitrification. First forming nitrite, I. Second, we form nitrate. Who's doing this? Bacteria. What kind of bacteria? Nitrifying bacteria. Who can the nitrate be given to? Plants, and then animals can eat the plants, and then the animals and the plants die. Who works on them? Decomposers back into ammonium. Another way to get nitrate. So you're going from N2 to NO3 minus, right? Directly. You're skipping all of those other steps, right? And then if I want to return this, instead of giving it to a plant, I want to return it to the atmosphere, I use denitrifying bacteria. Okay, and they return it back into the reservoir. Question? No. Okay. And that was the last cycle. That's it. Questions, concerns, issues? All right, that's it. Have good evenings. That was 33 minutes of fun. Have a piece of toast with peanut butter on it. Yeah, peanut butter, and then dice up little bananas and put that on the peanut butter.